going to continue the topic started by my colleagues, Diana and that guy from the data robot, Joshua. Yeah, all the perfect talk on Keras. So we are like giving you a lecture on the deep learning and machine learning and all these new and shiny things. And my shiny thing is named Building Decent Named Entity Recognition for the Ukrainian language with the help of deep learning magic. Hooray! And it takes a little bit of effort to decipher it. So first of all, what is the named entity recognition? Named entity recognition is a kind of machine or model to which you can throw the raw text which was unseen by that machine, and machine should identify in it some named entities like persons, organizations, locations, and miscellaneous things. Of course, it's not named entities, it's not only organizations. You can train a model which will learn to identify the names of diseases and drugs, and there are like a lot of names of drugs out there, and it's quite difficult task either. So we've managed to understand the first part of the name of the talk, the name entity recognition for Ukrainian language. And by the way, it's a little bit weird to talk about Ukrainian language in English, but well. And the second part, with the help of deep learning magic, this is how you do it. And the thing is, with current state of technology and all this hype of the deep learning, we've now got like a perfect tool belt for any practical situation to deal with text, images, sound, generation of images, processing and pre-processing, and question answering, and machine translation. All of that is done with these little tiny neurons. Even Shia LaBeouf was processed by some nasty neurons from Prisma application. And it's really easy to come up with a solution in just no time. It's like, zhoo, and you've done. So basically, let me just jump to conclusion, jump to the solution of the problem. Here we go. It's, I don't know, 15 lines of code, even with my weird indentation. And that's basically it. That's the model which you can train to then identify named entities. So now we can go and have some drinks. Yeah, okay, sorry. It wasn't really fair, and if you bear with me for another half an hour, probably, maybe 45 minutes, who knows, I will show you how it works. But the general idea here is, you know that joke about the perfect English loan? How to get yourself a perfect English loan? It's easy. You find the loan, you get the garbage and like old trees and stuff like that and roots out of the earth. You seed it, you plant some grass, then grass will come up, you will water it, you will cut it off, it will come up again, and you will add some new seeds and stuff like that. And in 200 to 300 years, you get yourself a perfect English loan. Pretty much the same is with deep learning. So to get some job done, you have beautiful instruments, but to get there, you need to do a lot of homework. So let's start with detailed review of my approach to this task, which is basically a FASTTEXT embeddings and convolution network and bidirectional LSTM. And to be honest, I just picked all the like buzzwords in the deep learning, smacked them together, made a neural network, and was able to solve my task. Sorry. So this is the architecture in a nutshell. So basically, it's a diagram of the code I've shown. And we start with input data, which is windowed sentences. And I will give you some examples just to make sure you understand what to fit into this network. And then we are using the embedding layer. And Diana touched this particular topic of word embeddings a little bit, and I will give more insights on it. Then we will have the convolution layer, 1D convolution layer with kernel size of 3, and then 2 bidirectional LSTM with 64 units, or not nodes, units, and finally the classical fully connected layer to classify words into 5 classes. Okay, and as always in machine learning, we begin with the data. And the data for our task, it's the manually annotated data set made over the BRUK corpus. Let's again decipher this title like step by step. BRUK corpus is a corpus. Do you know what the corpus is? Corpus is a collection of texts in some language collected under some rules. Sometimes these rules are really strict, sometimes they are not that strict. For example, you might have the corpus of medical text, or like in the case of Tatiana, you can have a corpus of recipes of cocktails, or maybe recipes of butter chicken, who knows. So corpus is just a collection of text, annotated or not. And the friends of us, the Brown UK team, all shortened BRUK, they are working on the kind of Brown-like corpus of Ukrainian language, which has very strict rules for text inclusion. So they are only working on original, not translated Ukrainian language text, which are also like was published somewhere. So it's not like just some weird notes or some talks. It should be published like in book or in a journal. And all this texts are quite recent to capture the current state of the language, so it's not like from past century. And they have a variety of sources and authors and topics and genders, just to give like the very wide corpus to capture the current state of Ukrainian language. So we took their work, and they are quite collaborative and quite nice guys to work with. They have all this stuff, all their stuff available on GitHub. So we've downloaded their dataset, and we built a tiny plugin for another project of us, the crowdsourcing platform called VULIK. So we added the plugin which allows some people to annotate this text, and here you can see the example. It's like a sentence, одіозний український тенор Володимир Гришко, and someone already marked that Volodymyr Grishko is a person, and then there are organization Euromaidan and some organization VZ or stuff like that. So we added the plugin for our crowdsourcing platform. We found 3 annotators. We processed all the text from the BRUK corpus that they had so far with redundancy of 2, so each text was processed and annotated by 2 different persons. Then it went through the editor, my colleague, Vsevolod Demkin, who is unfortunately not there, but he is a good luck. And we've published our results on our website, Lang.org.ua, so feel free to visit it, to download the dataset, to play with it yourself. And here is a stats of this particular dataset. So it's 229 texts, and it's almost 200,000 tokens, words basically. And among of them, there are only 6,700 of named entities. More of them are persons, but there are also locations, organizations, and miscellaneous texts like the Bible, for example, which is also kind of named entity. And you can see one problem right here, because our data set, it's like 97% of it is just words. It's not named entities, it's words like blah, I don't know, who knows. The Sena or Arena Lviv is a location or organization. So we have very skewed, very inadequate data set where most of words has just one class, and this is not the class we are interested in. And I will be like giving you some insights on that later. Okay, so we've collected some data, we pre-processed it. So on top we have an example of the sentence which reads: «Спільними зусиллями влада та громадськість врятували і повертають до життя Київський велотрек». And Київський велотрек has label organization, and under each word you have this word index. So we made a dictionary out of all words in our corpus, and we gave each word its own personal number. And then to make it fit to the neural network, which usually deals with vectors of features, we run a moving window, and in the center this is the current word, and we also given the context, like words on the left and words on the right, and we also have the label. So the word in the center for this one has class known, and this word has class organization. So you can see basically how it works. And also we padded the sentences with zeros well, why I'm saying we if it was mostly me who was doing that. But anyway, so this is basically the preparation of the data we did. And then we just can't fit this into the neural network yet, because neural network, as I said, they are working with vectors, but not just vectors. It should make some sense. So please welcome word embeddings. And you can see the vector cat gazing at the word vectors here. So what's so special about word embeddings, and in general, how you can fit the textual information into the neural network? The common approach here is you go with one-hot encoding. It's like you have a dictionary that long, like 3 million of words long dictionary. And each word is represented by the vector, which is 3 million elements long, and this is very sparse vector. So if your word in dictionary has the number 100,035, then it will be the vector of all zeros and one element turn it on position 135. So it will be humongous, very, 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 very long vector with basically no information. And of course, if you're dealing with vectors that big, it will cost you a lot to train your network and to a lot of memory it will add. So instead, we will go with an interesting trick and use a guide over here. It's from Monty Python. We will do the word embeddings or word vectors. So basically, word embeddings, it's a collection of algorithms to transform these one-hot encoded vectors into the dense vectors. Sorry, not dense, but dense vectors. So you are taking a huge amount of natural text in some language, say the whole Wikipedia in that language, and you throw it into unsupervised algorithm. So you don't need to annotate, you just collecting all the text you can have, and then you throw it into some weird machine, and after 4 to 40 hours of some strange calculation, it will map all these words in these corpuses into some multi-dimensional space. So each word will be given its own vector, which is usually from 100 to, I don't know, maybe 1,000 elements big. And idea here is that semantically similar words will be mapped to very similar points. So their vectors will be close to each other in terms of cosine distance. And this is like the main idea. So I will show you some example. This is from the global vector paper. They've come up with interesting algorithm to calculate word vectors, and then they took the common crawl corpus, which basically like all text from across the internet, literally terabytes of textual data. They run it through the weird machine, and then they started to query it. And if you're saying, okay, give me the words which are most similar to the word frog, and it will return like frogs, toad, littoria, or something, and wren, and lizard, and pterodactylus. So, okay, lizard is like, makes sense, but a little bit from different sphere, but the rest is depicted here, so it's all frogs and toads. And the idea of word vectors, again, so it will learn, it will make the words which appears in the similar context, like in text about frogs, yeah, it will make word vectors which are close to each other. And it's not the only useful property. The other useful property, and not a single talk about word embeddings can be complete without this slide, is the relation between word pairs. So, for example, you have man, and this is like vector for a man, and this is a vector for woman, and the distance and direction between them are pretty much the same like the distance and direction between king and queen, or maybe sir and madame, or brother and sister. So it also captures this semantical information of relations. And you can see that word embeddings are much better than just one-hot encoding because of two reasons. First, it's dense. With one-hot encoding, you have like, I don't know, million element vectors, and here you have just 300 degrees vectors. And also, it will help you to generalize. Two vectors from the same context, they will have the similar vectors. So this way, the model can learn that, okay, it doesn't matter if it was man or say boy or say dad. So it's all like similar words and they can substitute each other. And this is why your model will perform much better. And over the years, there was quite a lot of different algorithms for the word embeddings. I can mention the CCA with the word2vec by Mikolov et al. And Glove, which I like. This is slides from Glove presentation, and also LexVec, which is like updated version of the word2vec with also coherence metrics. And the most recent research here is very nice thing called FASTTEXT. It came from Facebook, and this is why I make it stood. Oh, sorry, I have one more slide. One more slide. So also, just a quick glimpse, what is the textual data for embeddings. As I said, you should have as much of good text as you can to train the good word embeddings, and usual sources for this is Wikipedia and news feeds like Gigaword corpus for English. It contains 1 billion words from the news feeds of 6 most powerful news agencies around the world, but also there are some data sets from Twitter, and also this common crawl, this huge, humongous database of text crawled from around the web. And okay, of course, for English language, we have plenty of sources, and you can download all of them. For Ukrainian language, we don't have too much. So basically, as usual, we have Ukrainian Wikipedia, and Wikipedia is a great source of textual data because you can just download the whole Wikipedia on your pen drive and then process it. But also, in addition to Wikipedia, we crawled the data from the news feeds and also articles from the newspapers. And we've got like, I don't know, maybe 5 gigabytes of text from Ukrainskaya Pravda, Correspondent, what else? Новий час, та інше, ну, багато джерел. Also fiction and poetry, and we managed to collect a corpus which is 665.5 million of tokens, so like more than 500 million of words in it, and amount of sentences is also enormous, like 48 millions of sentences. And we also make it public on lang.org.ua, so you can go and download it. Okay, so back to the algorithm. Basically, we took this corpus and we tried to train all different embeddings using all these different algorithms, and then with help of Tatiana, who drove this part of the work, we created, and here I am saying we, but it's mostly her, we've made an intrinsic data set to test the quality of word embeddings, who performs the best, who captures the most of syntactical information, and by a huge margin, the FASTTEXT was a winner. And why it's a winner? First of all, because it's like bleeding edge algorithm from Facebook research team, and it's state of the art. And also it's very quick to train. You don't have to spend 40 hours. You just can spend 4 hours on quite a powerful server. And as I said, it outperforms the competitors, gives the best results. And a very interesting feature of it is that it operates not on words, but it also like slices them to chunks, and it can learn morphological features, and then it can generate the word vectors for unseen, for unknown words. So if you throw in the word which wasn't seen, wasn't even in the corpus, you use it to train your model, and FASTTEXT will be able to understand that this word is probably has the same structure like the other way, the other words has, and it can come up with a word vector representation for this word, even given the fact that the algorithm haven't seen this word yet. And this will be quite a good word vectors, much better than word vectors, quite better than word vector just for unknown word. So this is why it stood out. And given these features from word embeddings, FASTTEXT word embeddings, we were able to train the model with no extra features, no manually created features, no gazetteers, no dictionary, no post-text information. So we just took those vectors, didn't embellish them at all, and the result was outstanding. So lovely. Okay, we finished with data preparation and short lecture on word embeddings, and let's start with the implementation. And to be honest, the most of the implementation I made while being on a business trip in Cambodia, talking to some Cambodian bureaucrats about assets declarations of Ukraine. And while I was like giving a presentation, my laptop was calculating some weird models and running some tests. Okay, back to the slide you already seen. We are now like here. We talk about the pre-processing of the data and the embedding layers. Now we will talk about real deal. So next in our architecture is 1D convolution layer, which basically does this. It takes each trigram, like each 3 consecutive words, and it runs it through 64 filters. So for each triplet of words, we will have the vector of 64 real numbers, and basically it effectively compresses the 300 features from word vectors to 64 features, but the features that will also capture the relations between consecutive words, and also to map them to the features that we already need. So it can learn some features of these words from the word vectors. And usually 2D convolution is used to pre-process images and identify, like, is it plane, or is it a bird, or is it a truck? Sorry, I ran out of coffee almost. So I can collapse at any time. Let's speed up it a little bit. And this is just like tiny addition to compress all this vector information and to capture the relation between consecutive words. And then we are throwing the results into the long short-term memory, so-called LSTM, and luckily for me, Tatiana gave you a glimpse on how it works, the long short-term memory cells. But the key idea, just to reiterate, maybe you were having a coffee or attending different talk, LSTM is a special kind of recurrent neural network. Neural networks that can work on the sentences, on sequences of examples, like words. So it not only operates on the current word, but it also maintains the history of what being said before. And the good thing is LSTM is capable of learning long-term dependencies. Like, it remembers what been said already in the first word in the sentence, and it maintains this information, contextual information. And also, LSTM has a state-of-art performance in natural language processing, speech recognition, and machine translation. And if you had the chance to read some of these Buzz articles about Google Translate being upgraded for English to French and some other language pairs, with help of LSTM model, they managed to outperform all the machine translation models they had, and now it even can compete with a human being, and probably can outperform me, and I'm quite bad at Russian to English translation, for example. And just to make things a little bit fancier, we decided to go with bidirectional LSTM. So bidirectional LSTM not only reading the sentence from beginning to the end, because sometimes, especially in languages like Ukrainian, there are dependencies between words which are going in both directions. So the subject and an object can be in the beginning of the sentence and in the end of the sentence, or vice versa. So to capture also this information, there are like two layers of LSTM cells. One reads it from one point to another, from beginning to the end, and one is reading from end to beginning, and then the results are concatenated and then can be processed by the consecutive layer. And it also improves quality of NLP-related models, but basically we added the bidirectional LSTM just because we can, just because it's so easy to do with Keras. Okay. Oh no. Penn and Teller will wait a little bit. And then the result of LSTM is passed to some kind of very, very classical, very traditional, fully connected layer, which will classify the results of LSTM layer into 5 classes. Like this word is not a named entity, this is an organization, and this is person, stuff like that. Okay, but as I said, it's easy, but not that easy. So there will be some tricks that we come up with and that help to solve some problems. And this is Penn and Teller. Do you know who is it? Do you remember? From my childhood to magicians. Love them. So first trick is unseen words. Like we are training our model on a corpus just like 129 text, which is very small amount of data. But we need to deal with text that wasn't seen by the model yet. And of course, those texts can have different unseen words, different names and organizations. In Ukraine, we have like 1 million of companies in the company register. Of course, we can't like have a model which has them all. And the good thing about FASTTEXT, and by the way, they have the beautiful Python wrapper. You can just load your model into memory, and then you can query the words, and word Butявka is not known by that model, and it wasn't in the text, but still it can come up with a pretty decent vector, which will probably place Butявka somewhere near to Bukashka and other tiny creatures. So FASTTEXT can generate word vectors for unseen words, and that's nice. The next problem is, well, it's a little bit not complicated, but like a little bit closer to the bare metal of the neural networks. When you are doing training on word embeddings, all the modern neural network frameworks like TensorFlow, Keras, I don't know, Caffe, Torch, they will have a utility layer called word embeddings. This is basically the layer in which you can put your word vectors, and then instead of passing the word vectors to the input of your model, you just said, okay, this is the word number 169, and it will look up it for you and find the proper vector and pass it down the line into the neural network. And it works, but it works on the dictionary, so it can work with unseen words. What you can do here, you can, instead of passing the word number from the dictionary, you can pass basically the word vector from, say, FASTTEXT, like you can, oh, sorry, crap, I'm sorry. Я что-то нажал, и все исчезло. So you can pass the word vector, the vectors you obtained from the FASTTEXT model, but still, instead of one integer, you are passing like 300 of floats, and this requires much more memory, and this will be much slower to train and converge. So what can you do? And I did exactly this. I made some kind of head transplantation. To train the model, I just put the embedding layer and used that word indexes to put in it. And then I've created the very same model, but the first layer, which was embeddings, I just thrown away. And instead, now I am accepting the list of word vectors. And then I just took the vectors, the weights from these layers from the model I've trained it on with embedding layers, and I've transplanted them into this recipient model and made it work. So now it can work. It was trained on like dictionary, but now it can work with unseen words. And final problem here is that I already spoke about it a little bit. The classes are skewed. We have the data set which mostly consists of words which are not named entities. And as you can see here, we have only 3% of named entities in this data set. So what that means, if you come up with a very simple classifier that for each given word will just say you, it's not a named entity. It's not a named entity, it's just a simple word. The accuracy of this classifier will be 97%, which is pretty high. But that classifier doesn't make any sense, right? And the other classes are quite rare. So to make that model perform beautifully and to make it possible to evaluate the results, there are a couple of tricks. First of all, you can provide the class weights. So you can say, okay, this is the class I care the less about. This is a class just a random word, so its importance is like, what, 0.01, right? And this is the class which is the rarest one, and we should take it very, very cautious to work with it, and it's a precious information. Please be careful with those. The same applies for other 4 classes. And another trick here is that if you want to measure the performance of such an algorithm, you can just use the accuracy, because as I said, the model which just can say it's not a named entity, it will give you 97% of accuracy. Instead, you should go with also F1 measure and precision and recall, which is the metrics that are suited for this particular task. I am not going into very much of details of them, but I encourage you to take a read on Wikipedia on that, just to show why it makes some difference. And now the slide with a cat, the results that we've got. And result from real-life example. This is the performance of the model on the test data, which wasn't seen by the model yet. So the accuracy is almost 100%, and F1 score is 86, 0.86. The precision is very high, so if it captures the named entity, it identifies it in a correct way. But recall is 76%, which means that not all of named entities are captured. But still, it performs quite in a good fashion. So here we have a phrase which I just ripped off from the news article from the last week's terract in the St. Petersburg, and you can see that it correctly identified the entities like European Union and Federica Mogherini and St. Petersburg. And of course, the model never seen the text like that, never been taught to deal exactly with these words. It probably doesn't even have these words in the vocabulary. So it's nice. And now we can also talk about some alternatives. Basically, what I did here is that I took the data I had, and then I applied some model, which I just collected all the buzzwords and stick them together with help of Keras and run it on my laptop. But of course, it's not the only model which you can use. First of all, you can come up with even simpler model which performs as good as mine, or maybe even better, but it will consume less memory and be quicker than mine, because mine is quite big. The good idea here is also probably to try to not classify each particular word, like, okay, this is a name and this is not a name, but instead we can just classify the beginning, the middle, and the end word of the named entity. So, and it will perform in 2 stages. First stage, out of this raw text, will just identify the chunks which the model thinks it's a named entity, and then we can take this named entity chunks and use another classifier which will say, okay, this is just a name and this is just an organization. And for this task, we have much bigger data sets available. For example, we can crawl or maybe find in some public places or maybe from Wikipedia, we can collect all the names, like million of real names, and we can toss them. We can, like, from the full name, we can generate the name and the family name, or just take the name or name and the отчество, sorry. Patronymic, yeah, correct. And we can do the same for the companies. We can grab the registry of Ukrainian companies. It's like more than 1 million, maybe 1.5 million of company names, and we can use it to train that model too. And just to supply the model with some negative examples, we can grab some random chunks, random words, which we know that is not like named entities at all. And this model will have much more data to be trained on, and it will probably perform even better. But again, it's like always with deep learning, it's an open-ended question. You can push it more and more and more and more and achieve more results, but someday you should stop and like start doing the real stuff. Okay, this is pretty much everything I've got today, and I also should say a huge thanks to these people. First of all, BIDIRECTIONAL, who is like deep learning mad scientist. If you ever meet him, he is thinking about in a hyper-parameter space all the time. He can bend it, he can stretch it and apply all different strange and weird algorithms to it in his brains. And Vsevolod Demkin, my partner in crime and Lenkor UA, and Tatiana Kodlyuk, who gave a beautiful speech on pretty much similar concepts today, and also Andrei Rysin and his whole BRUK team who are working on this Brown UK corpus, and also Andrei Stesin and Andrei Malenko, who gave me some servers at my disposal to train some models. And this is now the real end. And I'm happy to hear some questions if you have any. Please, don't be shy. Lunch is ahead.
Yeah, I have a small question about FASTTEXT.
Yes.
Like you said, it can predict the vectors, and it is based on morphemes, yes, if I'm correct?
No, it's not based on word-to-vec, but it can, sorry.
Morphemes like the root of the word, yes, on that stuff?
On morphology, yes.
Morphology, yes.
I think it just slices the word in some tiny chunks, like triplets of characters, and they'll then learn from them, and probably it also brings it down to the prefix and suffix like that. But there are humongous paper on that, which I don't have the time to read yet.
Yeah, okay, so my question is, the languages are quite weird. There is Chinese language, Arabic languages. Does FASTTEXT give good results on prediction in that weird languages?
I can tell about the about the Chinese or Arabic, because I haven't had a chance to speak to the people of who is doing the research there. There are some vectors trained by the FASTTEXT team on the Wikipedia, but I don't know if Chinese or Arabic languages has some intrinsic data sets like the data set we have to measure the performance. But I've heard from one Turkish guy that it performs much better than traditional word-to-vec, pretty much by the same reason, because Turkish language has a lot of inflections, a lot of word forms, just like Ukrainian and Slavic languages do.
Okay, thank you.
You have one example with word frog and all similar words that related to this frog. How it was made? So it made manually, or it is based on some context was like found in this?
As I said, all word vectors, they are basically trying to learn word vectors using the context information. So it can be co-occurrence matrix, basically a huge, very sparse matrix, which against each word pair from the dictionary, it says, okay, this word co-occurs, so have been seen in the data set close enough, like 5 times, and this word co-occurs like 1,000 of times. And basically, the idea here is that it uses contextual information just to come up with vectors, and this means that in this particular case with frog, the words like frog, frogs, toads, lizards were used in the very same context. Maybe it was like articles on about nature, or maybe it was a scientific papers where various species of frogs were described and how do they eat and populate and where do they live. Maybe they live like in the very same conditions, maybe it's like somewhere near the river. So all of these words had the pretty much similar context, not the same, but they've been like seen in the very similar places, in a very similar texts. And this is how model then come up with the vectors which are close to each other.
And how scores assign it? They assign it based on context, or like how system decide what score to give?
Well, it's a little bit complicated, and it also contains a little bit of magic. But basically, there are a couple of approaches here. One is you take this co-occurrence matrix, and then you run single value decomposition on it. So basically, you are trying to squeeze this huge matrix to the matrix size of like 300 to 300, and then you take the main diagonal of this matrix, and this matrix, this diagonal will have the best representation of this bigger matrix on this given that size. So it just takes all this huge matrix and compress it with linear algebra magic, and will produce you some vectors, which apparently makes some sense. And another approach here is to train a shallow neural network, where you are throwing the words seen together, and you are trying to make that model to predict the words. So you are throwing the word like, I don't know, river, and you say, okay, this word have been seen in context of forest, so river and forest is like the common words, and then you just strip the coefficients from this hidden layer of this shallow network, and this will be your word vectors. But again, it's like not a topic I can cover in 2 minutes. I encourage you to read some articles on that, and if you've been to this previous lecture from Tatiana, I believe she had some very useful links and very good explanations on how it works.
Thank you.
You can just yell at me if you want. Thank you.
What is the practical aim in the project, and where are you now compared to English? For example, what is possible in English that is not yet possible in Ukrainian with this technology?
You mean what is possible for English but not possible for Ukrainian language? Okay, so twofold question. And
yeah, in the context of all this work and the corpus. And
I got you. I will give you the answer. So the practical context, as I said, when I started doing that, at least 3 different companies contacted me as an expert in this field, which is quite a nice quite a nice word, but I'm not an expert by any extent. So the companies, the real companies, which are running real businesses on the analysis of the informational space of Ukraine. So some of them are working for politicians. They might be interested in daily slices, daily like reports of what is being discussed and who is being discussed in conjunction with who, and what is the tonality of news articles on this particular politician, and how the politicians migrating, I mean, how they're becoming close and far away. Because if you have the article which mentions, okay, say Poroshenko and Kononenko, it happens quite a lot now, but it haven't happened like quite a lot of time, 3 years ago. So now you can deduct that something is going on, so the informational space is shifting and changing its shape. Speaking of what is possible for English language but not possible for Ukrainian language, the problem here is it's not about the algorithms. We are basically standing on the shoulders of giants. All of this work, it's been done for English, and some of very early attempts to make an name entity recognition, they were made like 20 years ago for English. And so machinery is there, it's done. You just need to collect some data and to train models and to take into account the difference between languages, of course, but still the task is 90% done. Just to unlock it for Ukrainian language, you should collect some data. And once you've collected that data, you prepared it, you got it basically for free. And for English, it's all, for Ukrainian language, for example, we just like scratching it, but for English, it's possible to, say, find the relations in text. So you can train the classifier, which will say, okay, these two companies mentioned in this sentence or this paragraph, they're not just two companies, it's a mother company and a sibling company. Or they are doing a merger, merge, or maybe they're like one of them just got acquired by another one, or maybe one just went bankrupt. Or you can extract extra information from the text that this guy is the head of this company, and this will be done on the raw text. So so we are extracting the knowledge from the raw text, and we have plenty of raw text. Internet is full of raw text, and we just need to learn how to convert it to knowledge. You can also infer how to deal with tonality of text. So you can not only find all the news about particular person, say the candidate on presidential election, but you can also say that on this particular day, after this event, the reception of this event in the press was mostly negative. And again, you will get this information again from raw text with no manual intervening. And when you are working on this high scale in Ukraine, I believe there are thousands of news entries appears every day. You can have quite a nice overview, bird's-eye view on the whole informational field. The same can work for brands. So what is the reception of the brand? What is the reception of, I don't know, new design of the Coca-Cola bottle? Is it good? Is it bad? How should we react on that? So this is just the tiny examples, but of course the field is much, much bigger. You just seen how guy applied pretty much the same machinery to identify from the name of the good and the photo of the good, the class of the good. Yeah.
Okay, very quick question.
Hi. You said you used convolutional layer to reduce the dimension of the vectors. What is the purpose of the decision? Does it reduces the accuracy of the solution?
No, it doesn't reduce the accuracy of the solution. In my opinion, it gives some boost to this, to the accuracy, mostly because that convolution layer, first of all, it basically from 300 dimensional vectors, sorry, this one, yeah? From 300D vectors, it will only compute 64 vectors, but those that are useful for the model. So it's like the process of natural selection. And also it can combine the vector information from consecutive words, so you will also have this information of cross-words relationships in this window of 3. But as I said, if I just will remove this layer, I believe that model will perform on a pretty much the same scale. It just was funny to play with all these layers, and this is how it ended up in my final model.
Okay, thank you.